How did things go last time? Yeah, it was nice. Just funny. Funnier than me. Tomorrow will be the secondary open house. So this one's for folks who can't make it to the Thursday, the regular Thursday ones. So we'll look at the moon tomorrow. I don't know when the sun goes down. I think it's like near. Let's just find that out. Yeah, they do. It'll be. No, there won't be another one this Thursday. So the next one that is on the schedule is the one right before homecoming. Thank you. Yeah. And then we have another one for homecoming, which is wait. November? No, I think so.
Yeah, there's one in October.
Okay. So there's one on a Saturday and there's one on a Thursday in October. It's on the calendar. I'm just really bad at it. The sun goes down at 6:30. I guess that's what happens. Sun continues to set earlier and earlier during the fall. Okay. So that means the sun goes down at 6:30. Probably dark enough to see the moon like right away. But tracking with the telescope is a little annoying. So you want the sun to kind of not be super bright because it's stars. If you went last time or the time before that, you'll remember that from those telescopes. We'll have some projectors set up because just looking on a single iPad sometimes doesn't work as well. So we'll project the whole moon onto the wall. It'll look really cool. So come like 7:38. Yeah, at your own discretion. If you can get time off that. Maybe next week? I haven't written it. Is that true? Oh shit. Hold on. Let's verify that before we give everyone a heart attack. Oh shit, yeah. Yeah, so. Okay, so this is today. Getting through the climate atmospheric part is going to be, it's going to take as long as it takes, right? We kind of saw that planetary geology went a little long. We'll probably keep it at the same time of the semester. That way it's sort of like midterm as opposed to like 3/4 of the way through. And then you're like, I don't even know how I'm doing in the class. The only thing that would probably be cut out would be, stuff about either greenhouse gases, the terrestrial environment that we'll talk about the basics of an atmosphere today. We'll talk about the way that we heat the atmosphere and the dynamics of the atmosphere and how it relates to, example, distance from the sun. Okay, so we'll tie it back to those planetary geology concepts. And, it says cover up to chapter 10. That's probably exactly where we'll stop. So anything about Jupiter's atmosphere, anything about like icy moons, even though those chapters like icy moons comes later, you'll see that they're right here, 11.2. So all of this material up to chapter 10. Does that make sense? Okay. And then I talked a little bit before about how I like to do my exams. They'll be take home. Everyone's like, yay. Except for they won't be like fill in the number. They'll be like write words. And you're like, oh. So in the lecture tutorials, you've gotten really good at like explaining your thought process, right? You're really good at that now. So that's the skill you'll be using. Okay. You cannot work with one another, obviously. If I see 2 exams and you use the same words in the same order, that's called cheating, right? Okay. If you go online, let's say there's a website that most people know about in college, and you post the exam and you say, can I have some help, please? That's called cheating, right? We're not going to do that though. We like me, right? Right. Okay. Other questions? I will recommend that if you don't have these lecture tutorials, or if you haven't looked at them, do have a look at them. If you haven't done the homework, do the homework. Those are relevant. If you haven't done any of the reading, have a look at the reading. A lot, because it's open book, open note, you will have access to all of your own stuff, right? And so a lot of the questions, I'm going to give you a week, right? You're basically going to have 5 separate topics, of which you'll have 3 subsections. And of those 3 subsections, I will ask you to rank which you're the most confident in, the middle confident in, and the least confident in. And then you will get more points for the one that you claim you're the most confident in. Pretty cool, right? Okay, we'll practice this. I'll bring an example of it. And I guess I'll give it to you on this day. That's early next week. If you have questions on the exam, you can come to me, you can ask me questions. I do know how to answer questions. If you ask other people, that's totally okay. Just, you can't say, this is what I got, and then like ping the group chat, right? Because they need to show their own worth. So this is especially problematic because if you have a great explanation, and then someone copies you word for word, you both look like you're cheating, as opposed to one person who might have been helping out, and then the other person kind of got, ahead of themselves, right? Yeah. What would be take home?
I know, but like, very difficult time and midterm finals and stuff like that.
Oh, no, I'm gonna hand you a piece of paper,
Oh.
and you're gonna write on it, and then you have a week to take it home, and then you bring it back. Is that crazy? I don't know. Can I not do that? What? You have a week, yeah, full week. But here's what you don't do, okay? You give people something a week, and this is why I always wonder if I should do it this way. Give them a week, they're like, oh, great. Right? They never even look at the exam. Okay, and then it's 12 minutes before class starts, like, oh fuck, I'm supposed to do this. So the first thing you do is you look at every single problem. You're like, oh, I can do that. Yeah, no problem. Oh, that one I don't really get. I'm gonna read the book again for that section. Oh, that one, no, that's stupid. I don't like that problem. Right, and you walk through it, you tell yourself, okay, I can do this or I can't do this. And if you can't do this, you have 3 office hours to go to, right? Okay, everyone in agreement? Yeah.
Only the subsection that we rank most copies.
Yeah. This is always confusing for folks, and I'll explain it the day of. You'll see the version, and I'll put up the actual exam.
Will the final be something similar to the next one? Do like this something else?
The format will be identical. The questions I think will be cumulative, maybe. Depends on how advanced it is. Okay. Good questions. I didn't know we had an exam next week. My bad. Okay, let's talk about content. Questions before we get started about the content? No, I don't believe in scantrons. Okay, what was this? What is this? All right, good. Okay. What do I see in this picture? Clouds, very good. An atmosphere, very good. What's that? A reflection of what? A reflection of the sun. Remember when we saw Titan like 4.5 weeks ago? And we saw like it illuminated from the back, bouncing off those methane lakes. It's that phenomenon, right? Just on a different planet. Okay. Sorry, I'm moving whatever. We're gonna skip through these here. I don't exactly remember. So the Dr. Whitney went to a conference, so she hasn't given me you did lectures for us, right? Did you finish them all? Okay, I don't have them, so I need to get those from her. But you did these parts. Okay, confident. Raise your hand when you're not confident. Oh, okay. Do you want to go over these again? Okay, so really quickly, let's talk about this. 3 types of spectra. In the middle, this is hot stuff. When stuff is hot, it continuously emits at all wavelengths. I am currently emitting ultraviolet wavelengths, just not very many of them. I'm mostly emitting in the infrared. So if you were a snake, you can see me. Okay, I mean, you can see me now. Like, so you can see me with the lights on. Right. Okay. Here, wait, here, this is the barcodes that we use to check out atoms and molecules. Right. So we're all familiar with the idea of scanning stuff when we get to the register. There's a very unique code for every single atom and molecule. And it corresponds to the internal structure of those atoms and molecules. And so if I hit them with light, I can excite them, and then they will get relaxed and they'll give that light back. So this version and this version are basically inverse processes of one another. Here, I start with this rainbow. I have light at every wavelength, and then I pass it through the gas. The gas is going to absorb at those wavelengths. If I look off to the side, I'll see only those wavelengths of the gas. Okay, that's how we do composition of gases from space. It's how we know what the universe is made of without ever touching the sun. Okay, cool. Let's go. Come on. You did that? You did that? You did that. Yeah. Yeah, essentially. So think about it this way, right? These light bulbs are emitting light. They're bouncing off of me. That's the reflective process we talked about on last Tuesday. But absorption would be the reason why it's hot when you go outside. The sun is emitting photons and I am absorbing them, making me uncomfortable. Right? Okay, we're going to use this all now. Okay. You do this one? So what is this? Did you see this slide before? No, yes, no. Some of you have seen it, some of you haven't. Okay, so I'm going to ask what this object is. Okay, this is the thermal emission from the sun, highlighted here. This is less than the thermal emission of the sun. How do I interpret those two concepts? If I have a mirror and I place it, sun comes down, how does the light coming in compare to the light going out? It's what? The intensity here. So I have intensity, if the sun's coming in, something like reflection, that usually preserves the intensity, right? Whereas we just talked about these two different processes, emission and absorption. When we talked about what a strawberry's color is, what did we say? Everything but red. It absorbs all the light except for red, and red is reflected off. So we can actually tell what color this object is here. We see that it uniformly sort of absorbs in the green and the red. It's taking some light in. It's reflecting sunlight, but it's not reflecting as much green. Oh, sorry. It's not reflecting as much blue. So what is the absence of blue? We need like a color wheel, right? It's right here. What? Absence of blue. Red. Pretty good guess. But don't have blue. Green, yellow, red, orange. Those are all perfectly good answers. Right? No blue, probably red. Okay, so this tells me the color. And know that because this is the emission from the sun, This is the reflection. I know that it's reflecting a red color. Right? What the fuck's that? That's a weird one. This is another peak, but it's in the infrared. What is that? Peak in the infrared. If you were a snake and I turn the lights off, how would you see me? In the infrared, because I am currently emitting infrared light. I'm hot, and therefore I'm emitting light. That is the emission of whatever this object is, because it is hot. Anything that's hot will emit from the infrared. That makes sense to folks, or is that out of nowhere? Okay, so far we have two features here. Okay, here there's a continuous spectrum. It's like the sun, except the blue light was absorbed. And then over here, it's a solid object. It's hot. It's emitting infrared light. And I can tell you that it's about 225 degrees Kelvin. That might not be an intuitive number to you, so that's okay. But it's not my temperature. I'm hotter than 225 degrees Kelvin. Okay. What's the other stuff you see here? You see all these two big features. Anything else? The spikes, yeah. Which set of spikes do you want to point at? This one? Yeah, what the heck is that? Down spikes are, all right? Absorption. Okay, down spikes are absorption, because they're taking light away, the intensity is going down. And if you look down, you can see that here, right? They're dark in this wavelength region. Whereas on the other side, these are emission, because they go up and they look like that other picture we saw with bright lines in the ultraviolet. Okay. So that means if I have emission over here and absorption over here, then I must have an atmosphere. There's a gas cloud in between my line of sight, between me and this hot solid object that I'm looking at. Because that's the only way that you get absorption lines. Right? Okay, so you have a hot object here, solid. You have a gas cloud in front of it that's doing the absorbing, and it might even be doing some emitting. Because we know that solid objects don't emit single lines, they emit continuously. Right? I'm emitting a continuous spectrum because I'm not a cloud of gas. Okay. So we saw those. These are fingerprints of CO2 gas. You didn't know that ahead of time. I didn't expect you to. This is absorption of CO2 gas. And the last one.
The one on the way to the right, are those spikes, are those spikes going down?
Yeah, you can look down here too. See that part? Those are also down. So those are both absorption here and here. There's multiple bands where CO2 likes to absorb. Okay. And then the last part here, the up ones. Anyone want to make a guess? Emission? No. Anyone want to guess the element? You don't have to know this ahead of time. What's that? Did someone make a guess and I just talked over them? No. Okay. These are probably oxygen atoms. Oxygen, nitrogen love to emit over here in the ultraviolet. CO2 plus likes to emit over there. CO likes to emit over there. I've named all of these elements What do you guys think this planet is? Or object, if I should say. What's this object? Mars. Why is it Mars? Most of its atmosphere is carbon dioxide. It's red. Why isn't it Jupiter? Because it's solid, continuous spectrum, right? Okay. We good with this? It is indeed Mars. Come on. Ah. Okay, whoops, there it is. Mars. Thin, tenuous atmosphere gives you a little bit of those lines that we saw, both in absorption in CO2 and emission from the hot upper atmosphere. Mostly red. That's what the intensity look like. Okay.
The red is fine.
Well, okay, so the surface color itself, the reason why it's red, that comes from planetary geology.
Oh.
But that we're just talking about what this dip here is in the intensity. Okay. So why do we talk about this at all? Because even though we have been talking about planetary geology as a whole, you know, the part that we're potentially more interested in for us on a day-to-day basis, breathing in, breathing out is like that ability, pretty cool. Most things that we consider wanting to live need an atmosphere. So we're going to talk about atmospheres as a whole. And interestingly enough, they're directly coupled with sources of light. Okay. We're going to talk about a bunch of different things. This stuff here at the bottom, we probably won't get to before the mission, but this stuff up here we will. Maybe not this question, but this one here. And in particular, we'll talk about why the Earth so great to live on. And why you definitely do not want to go move to Mars, despite what anyone might try to tell you. Okay. The first question we want to talk about is what is an atmosphere in the first place? You've heard this thing like the greenhouse effect. How does that affect planets? And there is a nearby candidate that we'll talk about, Venus. Why is Venus so different from the Earth? If you recall from that planetary geology lecture tutorial, the temperatures of terrestrial planets seem to be going down as you get farther away from the sun, except for Venus, for some reason, has a 700-degree surface temperature. And you try to land on Venus and everything melts. Why does that happen? That's weird. Why is the sky blue? That's weird. Anyone know the sky blue? Okay, well, okay. So this is a reading question. Which of the following is the lowest layer of the atmosphere? The one that we are currently in. Is it A, the lithosphere, B, the exosphere, C, the stratosphere, D, the troposphere, or E, the thermosphere? You ready to vote with this? We're going to vote on 3, 2, 1. Okay. We've heard this word, so I think a lot of votes were cast for lithosphere. What is lithosphere again? It's what? Litho means rock, and sphere means sphere. So it's the rocky exterior to the planet. So it's not this one. Sorry. Exo, like exoskeleton. So we have an endoskeleton. Our skeleton's inside our bodies, but bugs have an exoskeleton outside. This is the top layer of the atmosphere. Okay, thermosphere. Do not expect you to have memorized this, but thermo means hot. This is a hot part of the atmosphere. Surprisingly, it's not at the bottom. Okay, so that just leaves 2 here. What's the right answer? Wants to explain the reasoning. Okay, I'll let you look at the reading to verify. Okay, because I didn't get enough votes there. Everyone's doing reading, right? Almost 2 or 3 people said yes, so I'm gonna go, no, not everyone is doing the reading. Okay, so here's the terrestrial planets, and what you can see here, Mercury, big atmosphere. What's that? Big atmosphere? No. Moon, big atmosphere? No. Mars? Not really looking like it. Looks like there might be something, but it's paltry compared to how cool that looks. Okay, Earth, big atmosphere, right? We just saw that it has devastating power, right? You live in Florida, you have friends in Florida, they have experienced firsthand how, I mean, there's an amazing amount of energy. When I say amazing, I don't mean in a cool way, I mean in like, holy shit, right? So even though it's thin, the atmosphere of the Earth, the way to think about it, if you take a basketball, you place one sheet of paper on top of that basketball, that is the thickness of the atmosphere. Okay, that's how you conceptualize it. And yet, we all live in that tiny piece of paper. Okay, so this thing is a huge atmosphere on a huge planet. Venus, it's got a bigger one. Okay, what's it made of? Not all atmosphere. Venus has a surface. We saw that when we had Venus's terrestrial geology, volcanoes, few impact craters, tectonics. Okay. Okay, here's the composition. You can write the funds in the book, open book, I'll write it down. Well, let's understand some of these parts. Here, Mercury and the moon. Not really an atmosphere. Rock vapor, it's kind of a weird thing to think about. But as stuff hits the surface, it makes it fly off. The lowest part of the atmosphere on these planets is the exosphere. Because anything that is liberated from the surface immediately leaves forever. So if you're a little water molecule, and you've been hiding in the ice for a long time, and you get hot enough and you sublimate, then you're flying away from the moon forever. Okay? Pressure, small. Basically non-existent. A bar, for example, is this measurement. It's a standard measurement. We like to center everything around how cool we are. It's one pressure at surface level at normal temperatures. Okay. So here you see, oh shit, that's a lot higher. 90 times higher pressure on the surface of Venus. Okay. But that's mostly CO2. 96% CO2, 4% nitrogen, no free oxygen. Whereas on the Earth, it's 77% nitrogen, 21% oxygen. This is why stuff is flammable here. Mars, 95% CO2, 3% nitrogen. So Mars and Venus actually have very comparable or similar compositions. The pressures are quite different. This one is much larger than the Earth, and this one is much smaller than the Earth. But ours is the one that we can breathe. Okay. Questions? We'll talk about why these are different. Okay. If I go up a hill, say to the top of that mountain range up there, are we more, less, or equal to 1 bar? That is to say, does the pressure go up or down? Or go up and down? Show me your fist when you're ready to vote. Ready to vote on 3, 2, 1. Okay. Lots of people said less than 1 bar. That's correct. It's harder to breathe as you go uphill. That's not just because I'm out of shape. It's actually because there's less air to breathe. You go to Mount Everest, When you're standing at the top of Mount Everest, you will need to bring your own oxygen. Or otherwise it's hot. If you're in an airplane and you're flying in the airplane and for some reason the cabin door opens, it depressurizes. What I said, depressurizes, less pressure, all the air flows out, and you die. Okay? As you move up into the atmosphere, the pressure goes down, harder to breathe. It also gets colder and then it gets hotter, but for different reasons. Come on now. Okay, so here's the big picture. We want to understand these terrestrial geology. We understand the terrestrial planetary atmospheres. And we're going to put this all together in hopefully a story that makes sense. And if it does make sense, you're going to come from the opposite side of that. There's mostly trace gases, rock vapor, solar wind stuff. We won't go over that in a lot of detail. But Mars and Venus is mostly CO2, a little bit of N2. Venus has a huge pressure, Mars has a small pressure. Venus is really hot. It's at 700 Kelvin. We actually already said today that Mars is about 255 degrees Kelvin. Earth, weird, got nitrogen, got oxygen, and it's got the right temperature for liquid water. I'm a fan. I like drinking water. Okay. We need to understand how atmospheres are created and how they evolve. Okay. So why shouldn't atmospheres matter? Just personal belief system. Why do you not give a shit about atmospheres? I've never thought about them before in my whole life. Is that correct? What about they're small, right? They seem like they shouldn't matter because there's like a tiny bit. We talked about the basketball analogy, one piece of paper on the top. Who cares? Right? That's a good reason why we shouldn't care. I don't extend very far compared to the whole radius of the planet. Right? Basketball is this big, this paper, tiny layer on top. The atoms themselves, they're not heavy atoms. Atmospheres are not made up of rocks, usually. Made up like nitrogen, oxygen, some of the lightest elements there are. And the total mass is tiny. Okay, compared to the mass of the planet. It's not where the mass is. Okay. But we've already talked about the fact that they have enormous consequences. So why do they matter? For the purpose of this class? Not just because that's my research. Yeah. Right? To be suitable for life. There's an atmosphere potential. What about in the context of geologic features? Presence of an atmosphere helps or hinders? Helps do what? Helps erosion, when we're connecting it back to that idea. But if you have erosion, you might have like gullies and streams. Yeah. Yeah, helps to identify if there's volcanism, right? You could be like, well, how did that atmosphere get there? Maybe it's outgassed from the interior. Very good point. Okay. We can also do this thing called greenhousing us, making the planetary circle warmer than it otherwise would be. Super convenient for us. It absorbs all that ultraviolet radiation that gives us cancer. I mean, not all of it, but we would die if we just left the atmosphere even for a couple of days. You have to use a lot of radiation blocking. Otherwise, you just get skin cancer right away. Very bad, not fun. It's really helpful at absorbing cosmic rays. Scattering of optical light brightens the daytime sky. So if you look at any picture from, for example, the moon with no atmosphere, you look back at the earth, the sky is black. We'll talk about why the sky is blue here, and that's from scattering from the individual atoms and molecules. Okay, we talked about creating wind and weather, low erosion, allows water to exist as a liquid. Right, and that might be the most important thing for us on a day-to-day basis. Okay, so let's talk about, we're gonna have to now talk about physics. I know, okay, it's okay. What does pressure mean? Not like I'm under a lot of pressure, but what is pressure? Forcing? Yeah, it's like it's a force on something, right? Okay, that's pretty good. So I put my hand like this onto this, I press down on it. Okay, I'm putting pressure on it. I'm putting more or less pressure than if I do it only on my finger. What's that? Yeah, more pressure with just a singular finger. So it's actually not only a force, but it's a force and an area. So for example, if I hit you in the face with an open hand versus if I somehow hit you with my finger, it's a hurt. Okay? Higher pressure, smaller area. Okay, same thing's true of gases. Okay, we're going to talk about gases, pressure, and physics for a few seconds. Come on. Where does pressure come from? Think about the air around you right now as a bunch of billiard balls smacking into each other on a three-dimensional pool table. They're just bouncing into each other, and as they bounce into each other, they bounce off of each other, and they bounce into other stuff. We're talking about all of the atmosphere right now, not specifically oxygen. Just going to think of them as nondescript atoms. They're not in a solid like this. Solid. This, even though you can't see it, there is in fact a gas here. Okay, and the pressure inside just comes from them bouncing off of one another. That concept makes sense? Okay. Which of the following does not increase the pressure inside a balloon? A, heating up the gas, putting more gas inside, shrinking the size, taking the balloon up to a higher altitude, or all of the above, increase the pressure. Let me know when you're ready to vote. This. The vote on 3, 2, 1. Okay, we got some votes. They're pretty spread out. Why don't you ask your neighbor what they got? And see if they agree. If they do agree, ask someone else. You disagree, so. You wanna? Sorry. Yeah.
I have to think about, oh, my.
So which of the following does not increase the pressure inside the balloon? When I say take the balloon, I got a balloon with a string. Not like, you're right, that's how you can get a balloon out there on your own. Metallic SpongeBob balloon, that's a bigger thing. Okay, folks, you ready to revote? All settled on the correct answer? Show me your fist when you're ready to vote. And to clarify, as was asked, this is of course a metal SpongeBob balloon. It's type that you get, it says happy birthday on the bottom. Okay. I'm walking it up this hill. I'm not lighting it up with a hot air balloon. Okay. Okay, let's vote on 3, 2, 1. Okay, good. All right. Almost everyone said taking the balloon up to a higher altitude would not increase the pressure inside the balloon. Let's find out why that's correct. Because you might have seen this one, you're like, oh, he never does all of that. You jumped on that one. It's a red herring. Be careful. Okay. So how do we increase the pressure in the balloon? Put stuff in it. More billiard balls inside the balloon bouncing into each other will increase the pressure. Stuff more people in this room. You're gonna start bouncing into each other. You're gonna get warm. You're gonna get uncomfortable. Okay. That's another way we can do it. What about if the individual particles, okay, they're bouncing around, if we heat them up, they will start to move faster. And each of the collisions will transfer that energy between the atoms and molecules more efficiently. This will push on the sides of the balloon and make the balloon increase. Okay? So that increases the pressure again. There's 2 ways. Okay, the pressure inside the balloon essentially is determined by the volume of the balloon, how many particles are inside, and how hot they are. So if we go back here, heating up the balloon, okay, that makes sense. Putting more gas in the balloon, that's the one I said to. What does this one do? Shrinking the size of the balloon? Yes, similar to that. So if you think about the same number of particles, you make it smaller. Now they don't have as much space, they bump into each other more. So let's take this entire class, we're gonna put it in a room this big, everyone's uncomfortable again. Right? Okay, taking the balloon up to a higher altitude, what does that do? It decreases the pressure because the temperature at higher altitude is higher or lower? Lower. That's going to decrease the pressure in the balloon. Okay. Okay, so let's talk about why there's pressure at all. My favorite analogy. Come on now. Maybe just because I'm tired. And these look like pillows, like lots of pillows. Okay, so when you are going to bed at night and you grab the pillows, you've got a bunch, obviously, and the one at the bottom needs to be fluff because it's been crushed by everything above it. The only reason why the air that we live in down here has high pressure is because all of this air above it is pressing down on us. Okay, the same phenomena is happening in the ocean. So if you get into the water, like pretty generally pleasant, but if you've ever gone snorkeling or scuba diving and you go deep, that water that's above you will start to crush you. And so, for example, if you want to go find where the Titanic sank, you can't just swim. You have to go in these really strong submersibles because the water pressure will absolutely crush you. Okay, if you're a lobster, you're fine. You're small. So you don't have air bubbles inside. Okay, since we have air bubbles, specifically these oxygen holders here, those get crushed. Okay, so if I transport you to Venus, and for some reason you can live through 700-degree temperatures, what does kill you? The pressure. The pressure squeezes your lungs and you die. Okay. So compressing the gas creates high pressure by squeezing them into a smaller area. And similarly, if I bring gas from the bottom, I bring it up, okay? If it doesn't have time to say release that energy, it's going to bounce around and it's going to expand. Okay? This is why hot goes up, cold goes down. Cold allows things to contract, not bounce around as much, and sink. Hot likes to move, oops, where am I playing? Okay, hot likes to move up, bounce off of stuff, and so it moves up. Questions about that? What? Okay, that's a very good question. Why do helium balloons float, but when I blow it up, it just falls down? Is it a temperature difference? Yeah, it comes out the same temperature that we are, right? Mhm.
And then.
Okay, so helium is often seen as cold because it comes out of these cold refrigerated tanks. But it's not inherently cold. Okay, so helium is inherently light. So it is only twice as heavy as hydrogen, which is the lightest element there is. Oxygen is 16 times heavier than hydrogen, right? So when we think about the air that we're breathing, it's actually quite heavy on a molecule per molecule basis. So the reason why helium things float is because if I take a balloon and I fill that area with enough particles, press out, fill this little ball, it is now displacing because it weighs less than other objects. And it's going to rise because of diffusion, like we talked before. Remember when we had oil and water and they would separate? Lighter stuff is going to go towards the top, heavier stuff is going to go towards the bottom. This is why a helium balloon floats. Okay, we're going to have to use both of those ones. It's a great question. The temperature causes things to go up, but also composition. Okay, right now we're just uniformly thinking about same atmosphere everywhere. Questions? Yeah. How come it's colder on the mountains? Okay, good question. So as we go up, let's assume that it's the same pressure everywhere. Okay, same composition everywhere. So, sorry, not as we go up, it's the pressure is the same this way, but not this way. Okay, so assume that the temperature is the same this way, pressure is the same this way. As I move up, okay, there's less stuff pressing me down. Because there's less stuff pressing me down, the interactions between the atoms and molecules are less violent. In the same way we can think about this classroom, having all of us in it, if I squeeze it in this direction, we're all bumping into each other, really having a bad day. But if I make the room bigger, then even when we bump into each other, there are less violent bounces. That's the idea of temperature. Temperature is stuff bouncing into other stuff. Okay, so as I move up onto a mountain, the pressure from above is going down. There's now more of the atmosphere below me than it is above me. And therefore, I don't have to bump as hard as this stuff. That answers your question. Anything else? Okay. Can we talk about surface temperature of planets for a second? We just talked about how atmospheres work. Now we have to combine that with light. Oh God, what? All right. Let's just remind ourselves. Sun gives off mostly blank light. The Earth reflects some, absorbs some, and re-emits blank light. Now those blanks should be filled in with something. What are those things? You're ready to vote in your face. Let's vote on 3, 2, 1. Okay. Okay, and I think everyone has a different answer. You want to defend their explanation? What do you think about 1? You don't like it? No, why not? Yeah. Yeah, so infrared is deeper. Okay, so you're saying that this part here is it's not hot. Right? Because there is that correlation between hotness and what type of light you get. Okay. So then you like ultraviolet, right? This is the answer? No, why not? Why not? Yeah, so now you have the answer. Okay. So can we see in the ultraviolet? No. Huh. So if the sun peaked in the ultraviolet, we would probably see in the ultraviolet. Because our eyes have adapted to be able to use the most information that we can. Okay, so we can throw out all 3 of these actually. Make my life way easier. Okay, so the sun actually peaks in the visible. Good job. Good eyes. Okay, so which one of these ones are there? There's just 2 choices. I don't know, you can flip a coin. Yeah. I think it's D. So visible light it's emitting in. And sun gives off mostly visible light. The Earth reflects some, absorbs some, and then re-emits infrared light. That's something. Why would it emit infrared light? Yeah. Yeah, if it's hot, it emits in the infrared. Solid bodies that are warm emit in the infrared. This is emitting in the infrared. This is emitting in the infrared. That's emitting in the infrared. That's emitting in the infrared. Okay. If it was emitting in the visible, we'd be in a lot of trouble. Okay. What emits in the visible? Example that we've used in the class before. What's that? A light bulb, yes, that's true. But like the tungsten filament inside of a light bulb is glowing at like 1,000 degrees. That's why you see light at all. Okay, so if the surface were 1,000 degrees, we'd be in trouble. Okay. Similarly, if you have an iron poker, you stick it into the iron. You stick it in the fire, it gets hot, starts glowing red. That's emitting visible light. That's too hot for us. We would not like that. Okay. Okay. We talked about that here. Here's the sun. Perfect. Wow, good job. You can right there in the middle. Redder star, you peek over here. Bluer star, peek over here. We still have visible light. Or peek over here in the middle try. Okay. Interestingly enough, we can make a diagram of how all this light interacts with one another. So here's a great example. Sun comes in, that's the yellow light. It's peaking right there in yellow. Oh, you see it as yellow. It's only illuminating half the planet though. That absorbs the light. heats it up. Makes it nice and warm, starts to live on, and then re-emits in the infrared. Now I'm showing them as red, but it's infrared. I just can't draw infrared light. Can't see it. Right? Okay. And the thing that's funny about that is you heat up the surface, it moves to the night side, cools off by emitting that light. Right? That's the process of radiation. We said that there are 3 ways to cool. Conduction, convection, and by radiation. This is radiative cooling. Okay? It's how we get rid of heat to space. Just let it go. The photon. Bye-bye. Okay. Here's an example. I promise this really happens. This is Saturn. This is a cool composition. This is a visible image overlaid with an infrared image. So here you see the rings, so edge on. The sun is shining from this direction. Okay, illuminating the surface. That's the night side. So if you stood here, it'd be sunset. And yet, when you look, okay, this shadowed region here is emitting in the infrared. This is still hot. This is, of course, the ring of Saturn creating a shadow on Saturn. Pretty cool. And then on the night side, it's mostly emitting in the infrared.
Why is it the color of the sun? Why is it?
Well, this is Saturn.
Yeah.
Why is it this color?
Yeah.
That's because its atmosphere is made up of hydrogen and helium mostly. And the reason why you see all this, like, the reason it's not uniformly colored, it's got huge storms on it. These are belts and bands of clouds. And those belts and bands of clouds absorb at different frequencies and give you sort of this weird color. As we look much closer, it'll become prettier. This is kind of a bad image because you can actually see how beautiful the clouds are. These bodies, all clouds. Okay. Okay. How do we talk about the structure of the planet's atmosphere? Now, remember how we talked about there's 4 planetary processes and they connect to these 3 different things. We're going to do that again, but this one is going to be weird. I promise you. Okay. I don't want to hear that. Almost. Okay. If you remember this, and you will, you'll be able to explain the structure of any atmosphere that we find that works with physics. Okay. How does this work? So this is increasing energy. The bottom you have infrared, what I'm emitting in right now. Okay, it's not hurting you. My emitting in the infrared, not posing any danger to anyone else. And what this primarily does is it makes things warm. It makes water molecules spin, makes them move around. It's how I heat my burritos in the microwave. Okay, infrared light, low energy, warming up molecules, making them rotate. I go up here, it's a little bit higher energy. Okay, so this is actually making me uncomfortable. Most visible light photons, they're simply transmitted. Blue is transmitted more than red. Sorry, scattered more than red. And we'll see that in a few seconds. Most of this through an atmosphere passes through, no problem. Okay. If it gets absorbed at the surface, though, it doesn't always come back. It gets absorbed, it goes into heating. And then the heating is re-emitted as infrared. Okay. They go up more, now ultraviolet, this is where it becomes dangerous. So ultraviolet light comes in. Let's say I start with a water molecule. Really good at saying, no hydrogen for you. Take one of those hydrogens off. Break apart the water molecule. So this is the destructive power of ultraviolet light. This is a heating source. Because after I smash into this water, it's going to start moving really quickly. And we talked about atoms and molecules bumping around. If I smash into one, make it into 3 things that are all moving quickly, that raises the temperature. Okay. And at the very top, the same thing's happening too, but even more energetically with X-rays. Okay. All of these things are coming from the sun, remember? So they're all hitting the atmosphere. So we can translate all of these processes into the atmosphere. And this gives us the structure. Okay. Up here, they're all hitting the top of the atmosphere. X-ray, ultraviolet, visible, a little bit of infrared. It doesn't give off a lot of infrared light. Let's talk about these ones. X-rays are coming in, they smash into particles, and they get absorbed. They destroy atoms and molecules in the top of the atmosphere. Same thing's true of UV, but it gets a little bit farther. Thankfully, not to the surface. But if you go visit your friends at Boulder or Colorado, which is a mile above sea level, you're high enough in the atmosphere that you're actually more likely to get a sunburn. Okay, so you're moving up. Now, not that high, obviously, up there. Okay. Visible makes it all the way down, thankfully, so we can see. Okay, so here visible light gets absorbed by our eyeballs, but mostly the surface. And then it gets re-emitted as infrared light. Now, infrared light really loves hanging out with atoms and molecules, like warming them up. And if you have the air right there, and heat up the air. Okay, this leads to a small layer right at the bottom of very warm air. So light comes in, visible light passes right through the atmosphere, warms up the surface warms up the air. That's why, if you notice, the hottest part of the day is not noon, when the sun is directly overhead. It's a little after noon, because the surface has to heat up enough to warm up the air. That makes us unhappy. Okay. Questions? Okay. This is a really important fundamental concept. So if you can go back and forth between this and this, you're good. Anyone see anything weird in here that they didn't like? Other than the whole thing? So this was temperature down here versus altitude. So this part, everyone was like, okay, totally cool. I get it. It's hot and it gets cold. Right? Everyone was totally cool with that, right? That's what you said earlier. But then you lie. It gets hot again as you go up. What? No one had a problem? That's where ultraviolet light is being absorbed in the atmosphere. It's heating up this layer. In fact, multiple layers in the atmosphere. As we move through them. We'll talk about the next one. But this one here, okay, X-rays smashing into particles, heat them up enormously. Two things are happening at the top of the atmosphere. The density is really low, the temperatures are really hot, really hot. Top of the atmosphere can be like thousands of degrees. Okay, down here, normal. Okay. Okay, so what's the troposphere? You're going to read the book, so maybe I shouldn't say this, but it's the lowest layer of the atmosphere. It's right here. It's where we live. Okay. Temperature drops with altitude, warmed by infrared light from surface and convection, and it's what gives us most of our light. This is where most of the atmosphere is by mass. Okay, but almost all of the atmosphere exists right here. What's right above that? Stratosphere, yes. So this part rises with altitude. Okay,
Where's the troposphere?
right here.
Oh, yeah.
Lowest part is troposphere. Stratosphere, come on in. Temperature rises with altitude in the lower part and then drops after the absorption of UV photons is done. So if you recall, oh shit, you may not recall. In the early 90s, we had a really big problem. They said there's a hole in the ozone layer. Might have heard about this. So there's a layer of ozone in the atmosphere, O3, called ozone. It's really good at absorbing ultraviolet photons. But a hair product that was very popular at the time, people used a lot of hairspray in the 80s and 90s, that are really puffy, uses something called CFCs, is really good at destroying ozone. So we were intentionally destroying ozone, not intentionally, unintentionally directly destroying ozone, which was letting ultraviolet light through. So the entire planet was like, oh, we gotta ban this. Banned them, ozone layer came back and it's actually protecting us again. But there was this giant hole in the ozone layer over the southern pole. I can show you. Pretty cool. Okay. So warmed by absorption, ultraviolet sunlight by ozone. Okay. Yeah, we have time for this. So convection, we've talked about that before. Yeah. Like this. So you have weather balloons. They'll go up certain heights. You can also send rockets. So if you shoot a rocket, you can put on board a little thermometer, which essentially smells the atmosphere. The funnest part is to like fly like blackbirds in military test flights up and down. Just stick a thermometer on there. They love doing that and they get to fly as fast as they go. Pretty cool.
But already talked.
You get satellites. This is how I do my job. You have to, for example, imagine you're at Mars. Can't fly a rocket at Mars and land on Mars. And like have a rocket to shoot up. So what you have to do is what's called using the properties of light itself to determine how hot it is. So we can fly satellites that can probe this region using the light that it's emitting. A little complicated, but I promise it's possible. Okay. Questions? Okay. Convection. Notable examples of convection include boiling water, we're good. What else? Oven, yeah, so convection oven, you have a heating element, forces air to recirculate and to bring that hot air to everything else. Miso soup. Take miso, sit it down, you see these little cells. That's where hot water, hot miso soup is rising and then sinking in other places. Okay. So what it requires is a hot and a cold section. If you've ever like try to make mac and cheese and you forget to turn the stove on, you come back 20 minutes later and you're wondering why your water hasn't boiled. There's no hot part. If it's cold and cold, no good. Right? What if I put the hot up here and the cold down here? Can I boil the water? I know no one's ever tried this, but just imagine it for a second. Why no? Because hot things rise. So for example, fluids, water, gas, hot things rise, cold things sink. So if I put the heat down here, these bubbles are hot. They go up here, they make this cold stuff hot. And then the cold stuff that's up here goes down here. That is circulation. That is convection. Okay. So if heat's at the bottom, you get convection. That process makes sense? So now, come on now. So based on the plot, where's the stratosphere, by the way? To this part? No, it's this part. Okay. Okay. So this part's the stratosphere. Can convection occur in the stratosphere? Okay. So from 10 to 50, from 50 to 80, so that would be from 10 to 50 here, here, or over here, or no. Vote with our hands. 3, 2, 1. Okay, interesting. Huh. I don't really have time to break up and think about this. I don't want to defend their anything. Anyone say no? Yeah, why not?
Going way thicker.
Mhm.
If you can do it, you can have it, line up, and then you have to.
Okay. Okay. Any counter arguments? Oh, you agree?
It's really.
Okay. Mhm. So this is the temperature profile, right? The red one? Do you have a different argument? It's the same one. So far, all votes for no. Yeah. Okay, colder to hot, from here to here? Yeah. So you think that's where it could happen? Any other arguments? Yeah. Wait a second. How does the boiling water work again? Where's the heating element? At the bottom. Does it boil if I put the heating element at the top? No. Where does this exist in this picture? Here's the hot. Here's the cold. So hotter rises. Right? And then it cools and it sinks. This is convection. That's why there's this little thermosphere. We see it in the troposphere. Can it do it here? No. So it's just chilling. Okay. It's not like rising to get hot. It's getting hot because you said UV photons. But what about above that? Here, now they're hot and they want to go somewhere. They rise, temperature cools, and they fall back down. So you have another set of convective cells between 50 and 80. Anywhere else? No, because there's nothing above the top of this. It's empty space. Okay. What's the answer? Yes, from 50 to 80 kilometers. Because I have hot at the bottom and cold at the top. Okay. So we're gonna go through, we're gonna break these down more. The thermosphere is up here. It's heated mostly by ultraviolet light. Starts at about 80 kilometers. Temperatures just rise. Sorry, not ultraviolet light, by X-rays. The top edge is the ionosphere. This is very, very hot gases that just don't need electrons anymore. Goodbye. And then you get above that, it's the exosphere. So like endoskeleton, exoskeleton. So this is the outer part of the atmosphere. And this just gradually fades into space. And here the temperatures keeps rising. Temperatures keep getting hotter and hotter because there's nothing cooling you down except for when you leave the planet. And you're getting bombarded with X-rays. Highly energetic light from the sun, heating you up, making you very uncomfortable. Okay, it's a warm heart by X-rays. Okay, a lot of light does get through. It's not very dense, so it's not like this is a protective layer at the top. This is in fact where we lose material. So it gets really hot and it evaporates, just like boiling off all of your water if you left it there for 30 minutes. Okay. Questions, comments, concerns? Yeah.
The thermosphere is where on there?
The thermosphere is actually right, it's in between these movies there.
Where's the exit?
Here's the exosphere. Okay. Any other questions? Okay. Thanks, folks. We're gonna leave it there. I know that's a lot of material. If you come up with anything later, you have any questions, feel free to come to my office hours or ask me. Yeah. Yeah,
I think